So I'm going to do another blockchain video today, and it's going to be all about what goes in a block header, in particular focusing on the Merkel root and how the transactions in the block are actually recorded in the block header and basically stamped for all time in a way that can never be modified. And it's going to go into also a few things that we haven't mentioned before, like SPV, so simple payment nodes, and all that kind of stuff. So I'm going to break down exactly what the Merkel tree does, what it's used for, all that kind of stuff. Please excuse my voice, I still have a bit of a cold. I'm getting over it quickly, but I want to do this video today because it's Sunday morning, it's the only time I get to do it. So, okay, I think by now this diagram should be fairly familiar, right? So this is our visualization of the blockchain, right? And we think of it as actual blocks that are stacked on top of each other. My first video talked about a physical analogy of boxes of checks stacked on top of each other, and all that kind of stuff. So this is our blockchain, and this is the database effectively that each node in the blockchain network stores locally. When I say database, so there's no centrally respected or authorized database. It's a consensus database which is duplicated across every node in the network. And the database basically groups our transactions into these blocks, which are logical entities in the database which have a pointer back to the previous entity. So if you've been watching my previous videos, you hopefully know this already. Now, in the last video, we started to talk about sort of the fact that the block header is hashed, basically, and that is used to basically, to rubber stamp the contents of the block. So we've been through all that, but we alluded to the fact that one of the items in the header for this block. I'm just going to zoom in here a little bit. So let's take a sample block. So the structure of the block is actually divided into the header, right? The header of the block, and then the body of the block is essentially the actual transactions that are in that block, right? The actual transactions that have been grouped by the successful miner, right? The successful miner of this block, basically, who pulled all these transactions together, solved the puzzle to find a block header hash that met the difficulty target, which we talked about in the previous video. So that's the header, right? And then the rest of the body of the block is the actual transactions. So sometimes it helps to think, okay, so where are these transactions stored? Where are the block headers stored physically? I mean, at the end of the day, it's a database. And if you download just gonna make some space here. If you actually download the Bitcoin client, right, onto your local system and run a full node, you'll start to see on your file system these files, right? So that you have file one. I think they're called BLK files, right? This is not the way they're named, but you'll see on your file system in a special directory, right, which is basically a data directory, right? You'll find these files start to download, right? And you'll find that there are shitloads of them, right? It goes up to it downloads all the blocks from the blockchain, but it stores them in these files. And that's the physical, that is the blockchain, right? So everywhere you see somewhere like blockchain.info website or anything that's reading the blockchain, the data is actually stored in these underlying files. Now, if I just zoom out again, so it's important to sort of, or it's interesting at least, to sort of consider how the data is stored. So as I said, each block, or the data is split up into logical entities called blocks. Within each block there is something called a header, and then there is the actual body of the block, which is the actual raw transaction data, right? The actual transactions. And they're basically tied together in this logical entity called a block. Now, as we know, the only thing that's actually hashed, right, to create the signature or the footprint for that block is the header, right? So it's everything in red here, and as we know, right, just going to zoom in again in a second. So the main things that go into the header, right, the main pieces of content are the previous block's hash, or let's say the previous block's header hash, which, as you can see, is a back pointer to the hash of whatever is inside here, right? And then you've got the nonce, which is the random number, or at least the numerical field that the miners are at liberty to play with the value, right? So that when they repeatedly hash whatever is in the header for the candidate block, they get a different number each time, and they keep iterating and iterating and iterating until they find a hash that basically meets the difficulty target, right? So, and that ultimately means that the hash is, if you look at the hexadecimal representation, it begins with a specified minimum number of zeros, right? And so they keep playing around with this, and so I know I'm kind of repeating myself, but want to make sure that the point is made clear. Okay, so we know that the previous block hash is really important because this gives us a way to link blocks together, so that if somebody, for example, if somebody tries to modify the contents of this previous block, I'll zoom out again in a second. So if somebody tries to modify the contents of this block here by maybe, let's say, adding a new transaction in there, right? If somebody tries to add a new transaction into the previous block, then what happens is next time this block is validated, right? The hash of basically this Merkel root, the hash of the transaction is going to change. This block hash, right, is going to be now a different value, right? And it's no longer going to be the same value as that. So going back, we just talked about if we change our transaction here, the Merkel root is going to change, and that's what we're going to talk about in this video. So the Merkel root here is a way to ensure that if you change anything in this list of transactions here, this value here is going to change. The Merkel root is like a fingerprint, a digital fingerprint of this big list of transaction data, right? So rather than actually storing the transactions in the header, we actually basically create a footprint and store that in the header, then we hash that, right? And that becomes the value that is pointed to in the previous block hash of the next block, right? I hope this is clear. If it's not, please leave comments below. I'm sure I can sort of iron out any questions quite quickly. Okay, so this video is really, well, before I carry on, I'm just going to give you a quick snapshot of exactly what's in the header from the O'Reilly book on Bitcoin, which I'll link below. It's a fantastic book, and I'll give you an exact snapshot, so you can see, because these are the main fields that warrant discussion. But so as you can see here, I've just basically taken a screenshot or opened a link, and you can see. You can see what the actual block header fields are. The Merkel root is the one we're going to focus on today. Timestamp difficulty target is obviously the number, the minimum number of the hash that is sufficient to meet the difficulty target. The nonce is that random number we talked about. Previous block hash version, the timestamp. We're not going to talk too much about that now. And then the actual, you can see the structure of a block is basically we list the block size. That includes the block header, right, which is all the information in that red box we're talking about, and then the number of transactions and the actual transactions themselves. That forms the body, and then the header is down here, right? So this is, if you like, you can see here all the different sizes in bytes of each part of the block. So if you're interested, then just pause that, take a screenshot. I'll link this down below as well. So going back to our drawing. So what's this magical Merkel root thing we've been talking about, right? What's this way of creating a representation which is only 64 hexadecimal characters long, right, or 32 bytes, that represents and records, or at least ensures the integrity of the list of transactions, both in terms of the number and the content of those transactions, right? So it's called the Merkel root, right? Now let's explain how it works. So if we, I'm just going to sort of, if we kind of home in on this block down here, right? I've just said, okay, so in this block we have 4 transactions, right? So the miner who mined this block, he chose to include 4 transactions. In practice, obviously, you know, Bitcoin blocks generally contain many more transactions than that. I'm just using this because otherwise the diagram is going to be a nightmare. So at the end of the day, miners are at liberty to include whatever transactions they want in a block. It's just that, and by mining a block with 4 transactions, they're not going to create or collect many transaction fees. But for simplicity's sake, 4 transactions, and so here's the header, right? It contains the previous block hash, which again points to the hash of the previous block header, which I haven't drawn, I have now. And then the list of transactions, the actual body of information listing all the inputs and outputs of the transactions is down here. And then in the header, we have the Merkel root that represents those transactions, right? So what is the Merkel root? So it's actually quite simple, first of all. So what we're going to do is we're going to basically just take these transactions, and I've sort of listed them across the top here, right? And so think of these as like just you know, the digital representation of these transactions, like the data, right? So we take each of these transactions, and rather than actually, because we could actually, you could think, well, if we just need to create a footprint of these transactions to make sure that the block hash includes a footprint of the transactions, so that if any of the transactions change, the block hash changes. You could put all these transactions in the actual block header, right? You could basically just go in here, right, and then just list all the transactions in the block header, and then hash that all together, right? So you could create a huge block header and just do away with all this completely, right? Just hash the whole block, and we'll come to exactly why we don't do that in a second, right? When we talk about the simplified payment nodes. So if we sort of zoom out again, right? So what we do is we separate the transactions out, right, as separate entities, and we pass each transaction through a double SHA-256 hashing algorithm, right? So we take transaction 1, we pass it through SHA-256 algorithm, we take the output, we pass that through SHA-256 again, basically creating a double hash, and then we record that value, right? And we call that H1, right? Hash of transaction 1. It's actually a double hash. Same with transaction 2, we create hash of transaction 2, right? So transaction 2 goes through a double hash, and then to create this. We do the same with 3, and we do the same with 4, right? So now we have double hashes of all our original granular transactions that we intend to include in the block, right? Then what we do is quite simple. This is the example of a binary Merkel tree, right? The binary Merkel tree. What we do is we take these transactions, these individual inputs, and we put them in pairs, right? So we say, right, 1 and 2, you get together. 3 and 4, you get together. Combine those 2 hashes together, right? That's this bikini bottom type drawing. Sorry, my drawing is not getting any better, but that means that we're combining these 2 together, and we're putting so we're just concatenating those 2 64 character strings in hexadecimal together, and then we're putting the result through, again, another double SHA-256 hash, right? So through one SHA-256 and then through the other one, and then we get the hash 1, 2 means that basically the hash of the hash of 1 and the hash of 2 combined together, right? And we do the same for these 2. We combine the 2 together, just one next to each other, and then we put the result through a double hash, and we get hash 3, 4. And then, because it's a binary Merkel tree, we basically split the result into pairs again. Well, because we only had 4 to begin with, and we've already split into 2 pairs. The results, there's only 1 pair remaining, so we basically combine those together, right? So hash 1, 2, hash 3, 4. We combine those 2 together. We put that through a double SHA-256, and basically, when we get to the bottom, as in when we only have 1 hash remaining, right? This is called the Merkel root. It's the root of the tree. So let's just rewind, right? So the tree starts with these leaf nodes. The leaf nodes are the individual transactions in the tree, right? And our tree here had 4 transactions, right? But in a real block, you might have 100, 1,000, or whatever we've seen in blockchain.info, you know, the blocks themselves in the real world, in real blockchain, Bitcoin blockchain at least, have, you know, many transactions, right? And it depends from block to block. But if you start with, so here we started with 4 leaf nodes, and then each leaf node has a parent. So the H12 is the parent of H1 and H2, and then basically we keep hashing the combined hashes together until we end up at one root node, right? That's the root of the tree, and that's called the Merkel root. Now, you might be asking, for example, what would happen if, let's say there was only 3 transactions in this list. So let's say transaction 4 did not exist, right? Then what happens? Well, in that case, because it's a Merkel tree, and it's a binary Merkel tree, we require an odd number of transactions to start with, so or at least an odd number of leaf nodes. So in that case, transaction 3 would be repeated, duplicated, right? And then that would go through the SHA-256. So that's just a small sort of corner case worth pointing out. But you get the idea. So basically, you start off with a huge number of transactions. You pair each of them up into pairs, and you hash each transaction first. Then you pair them up into pairs, combine those hashes, and then basically hash the result. And then you repeat that pairing process until you end up with 1, and that's the Merkel root. So is it obvious from this then that basically if so now I have this Merkel root here, right? This number, right, which I've populated in here, right? The Merkel root. Should make a different color actually. So the Merkel root I've populated here, and that's this value. That's this value here, right? So is it clear that if I go and try and add a new transaction to this list, and somebody comes and validates this block, basically by checking first of all what is looking at the transaction list, right, in the block, and then looking at the Merkel root value, is it clear that these two are no longer going to add up? Because that validation is going to involve doing the same thing, right? It's going to basically it's going to check the Merkel root by laying out all the transactions in the list in a long line like here, right? And then repeating this process and checking that the Merkel root that comes out is the one that's in the block header, right? So clearly you can't add or change the transactions in the block without changing the Merkel root. And because we hash the Merkel root as part of the block header, you can't change the Merkel root without changing the hash of the block, right? So effectively we've achieved what we wanted. We've achieved the same thing as we would have if we just basically put all of the transaction body, like all this massive data, right, for those thousands of transactions into the block header itself and just hashed it all together. We've achieved the same thing, right? But we've done so by only including this small or smaller 64 hexadecimal character value in our block header and using that to hash, right? So the question is, why do we do that, right? What's the point in this? And really, the main reason why it's done is to do with these. I mentioned it earlier. We're going to talk about it now. Is these SPV nodes, right? So sometimes, let's say certain clients, certain Bitcoin clients or Bitcoin wallets, devices that want to participate in Bitcoin transactions, they don't have the space, right, or the processing power to download and process and validate the entire blockchain, right? The entire blockchain, as we've seen on blockchain.info, is something like, it's in the order of 400,000 blocks at the moment, right? And it's going up all the time. That's a lot of data, right? It's tens of gigabytes of data, right? So you can't download that on every single device that actually wants to be Bitcoin enabled. So So an SPV node, right? What that does is basically it allows a so let's take an example of a Bitcoin wallet application on an iOS, also on an iPhone, right? So this application, we're not going to download the entire Bitcoin blockchain, right? We're not. But what we do want to be able to do, if we are transacting with somebody else, so let's say if somebody's sending me some Bitcoin, the fact is I'm really only interested in the transactions that affect Bitcoin addresses that are associated with my wallet, right? I'm not interested I'm not participating in this whole kind of amazing mesh network of validations and all that magical stuff where transactions get propagated around the world in seconds. I'm not participating in that. I'm only interested in the actual transactions that affect me, right? The addresses that are stored locally in my wallet. So what happens is those nodes, right, called SPV nodes, what they do is so if you remember the blockchain itself or the blocks themselves, each block consists of, I've just drawn 2 blocks here, the header, right, and then the transactions, right? So the header and the transactions form a block. Now these SPV nodes, they will download just the headers, right? Just the block headers, which is basically a tiny fraction of the overall information, because the thousands of transactions, including all the data about the inputs and outputs, that makes up the bulk of the data in the actual blockchain database. So they download the headers. That is sufficient information to actually to validate at least that the block headers point to each other properly, because if you remember, the block header itself is the only thing that's hashed, right? So, and it contains the link to the previous block header. So at least the SPV node, by downloading the block headers, it can validate at least that a certain block header is a valid block header on the blockchain, right? Because it can do the hashing locally and check that the previous block header can be found in the blockchain, and it can basically go back and validate that all the way back to the beginning. So, but let's take a very important use case here, which is that if an SPV node, so a device or something that has just basically received a Bitcoin payment, okay, let's say they want to wait, right? They want to wait for confirmation that a particular transaction that they've just done has been validated, right? Has been in the blockchain, right? So validated means it has appeared in a block, right? That it's been mined. It's been mined into a block in the blockchain, right? At that point, they know that the transaction has been validated by all the Bitcoin nodes, and it's been mined into a block that has been validated by a Bitcoin miner, and that block has been accepted, right? So they're waiting for this confirmation, right? So how do they? The question is, right? How do I prove that a particular transaction is within a certain block, right? So and it doesn't have to, it can be any block. The question is, has this transaction that I've just done, has it yet been mined into a block? And that's as simple as that. And the question can be answered as follows, because what will happen is, if I just zoom out a little bit, so basically this SPV node, let's draw the node here, right? So we've got our SPV node, and then we've got our whole network, right, of full nodes, and then and this connects to a full node, right, on the network, like this, which is part of the overall network, right? So the SPV node connects to this, and it says, is this transaction, right? So basically, I'm going to give you my transaction ID. Is it part of a block? And the full node, which obviously has a full copy of the current blockchain, will basically say, it will send it'll send back the SPV. It will send back the block header in which the transaction is actually found by the full node. So the full node looks in its blockchain and says, okay, where is this transaction in the blockchain, right? And so basically, the full node will find that transaction in a particular block in the blockchain, and it will send the block hash for that block header, right, in which the transaction lies, and it will send the Merkel path, right? And those two pieces of information, right, sent to the SPV node, they are sufficient for the SPV node to prove that that particular transaction is indeed in that block. And let's have a look at exactly how that happens, right? So our full node, right? So full node down here has been asked by this SPV over here. It's been asked, it says basically which block contains TX3. And by TX3 I mean the actual transaction ID of the particular transaction, right? The transaction hashes. I don't mean the string TX3. But so basically this is the transaction ID of TX3. So the full node has been asked by this SPV node, the simple payment node, which block contains TX3, if any, right? And the full node looks for, it's going to look in the blockchain that it has, right? The database that it has locally, and it's going to look in all the blocks to find which, if any of those blocks contain TX3, right? And let's say it finds it in this block here, right? So fantastic. You can confirm that this transaction is part of this block, right? Let's call it block 3, right? But again, the block itself will be defined as the block hash header, the block header hash, right? So the full node will say, okay, so yes, this transaction is indeed in block 3, and here's how I prove it to you as the SPV, right? The SPV node, which doesn't have the full transaction content of each block, but it does have all the block headers, right? So what it says is, right, so block 3 looks like this, right? And block 3 has the, as all block headers do, this is the header, right? For block 3, it has the previous block hash. It also has the nonce, right, which was seen earlier in the video, but it also has the Merkel root, right? So, and this we do have on our SPV, right? We do have this information on it. The SPV has all the block headers, but not the transactions, right? I know I'm repeating myself, but so the full node says to the SPV that this is for block 3, right? It says this transaction, yes, it does appear in the blockchain, and it is in block 3, right? So how does the full node prove to the SPV that TX3 was indeed in block 3? Well, it goes back to the Merkel root again, and here's how it works. If the full node says, okay, here is this is the transaction that we are trying to prove lives in this block, right? Block 3. So effectively we're trying to, and we know that the Merkel root of this block is this value here. So really, if we can say to the SPV, here's the Merkel tree representation information you need to prove that TX3 was in this block header, and really what you mean is prove that TX3 is actually part of this Merkel root, right? If you understand why it's as simple as proving that, because the SPV itself can validate that the Merkel root is valid, and because it can hash the entire block, it can include in the previous block hash, and it has a copy of all the block headers that it can validate all the way back to the beginning. So really it comes down to how does the full node prove to the SPV that TX3 is part of this Merkel root? And it's quite simple, right? What it has to do is to say, well, we both know so in this tree, both parties, they know the Merkel root, right? Because it's part of the block header. So we know this. We know this value here. Now, if here, I'm going to provide you with this value here, okay? And I'm going to provide you with this value here, then you can prove that TX3 was in this Merkel root yourself, right? So let's see exactly how that happens, okay? So just illustrated it over here, hopefully a little bit better. So here you've got the full blockchain with all of the individual transactions in each block, right? This is block 3, so it includes transaction 3. And then those same block headers are actually on the SPV as well, so they both have reference to this. And so we're now talking about how can the full node prove to the SPV that TX3 was indeed part of block 3 just by providing the Merkel root and the Merkel information about the Merkel tree. And so we said that basically by providing this number here and this number here, the SPV can prove to itself that TX3 has to be part of the underlying transactions that were used to create this Merkel root. And here's how, right? So basically, if we have H4, right? So the SPV can basically take, let's just draw this in dark blue. So the steps are as follows. Let's draw the steps one by one. So step 1, SPV knows TX3, right? That's the transaction we're trying to prove is in the block. So we're going to hash. So the SPV hashes TX3, and when I say hash, I mean double hash, right? So that gives us H3. So the SPV calculates H3. And we said as long as the full node has been able to return the Merkle path, which means basically certain key strategic points in the Merkel tree that the full node is capable of producing at any time, right? Certain values can be used in combination with the information that the SPV already knows to ensure that to validate that TX3 was part of this hash. So the first one is SPV hashes TX3, and then we look at the hash of TX4, right? So basically the first point on the Merkel path, and we hash and we combine. So combine 1 with H4, and H4 comes from the full node, right? It's as part of the Merkel path. Then take the output, right, of 2 and combine with H12, and H12 again was that other node that the full node sent back as part of the Merkel path, right? So combine with H12, hash that, right? And then bingo, So the combination of these two together, hashed, with this one that was provided by the SPV, that should equal Merkel root. So validate that the results equals the Merkel root. Does that make sense? So basically, the SPV only knows the Merkel root and the original transaction. It's a binary tree, so the full node returns only sufficient nodes in the Merkel tree, which the full node is capable of recalibrating or recalculating, at any point in time. Sends those pieces of information back to the SPV, and the SPV can perform the validation themselves. So they go right back to the beginning and they say, right, what's the missing node right at the bottom of the tree from the Merkle path that the SPV sent? Okay, fill that in, hash the two, combine together, take the next missing node sent by the full node, combine the two and hash, and do that all the way down to the point where you're actually hashing the last value and checking. And if you can validate that equals the Merkel root, there's no way that any other transaction than there's no way that transaction 3 could not have been part of that Merkel root. Right? At least that's as safe to say as is the integrity or the safety of the SHA-256 algorithm. And you know, collisions happen in SHA-256 theoretically, but it's one of the foundations on which the whole blockchain really depends. As in, you know, the whole network is really only as good as the SHA-256 algorithm. So we kind of assume that basically if we can use transaction 3 to replicate, to reproduce the Merkle root, then it must have been part of the original inputs to create it, right? So I hope that makes sense. So if we just sort of formalize what the Merkle path would be, right? We'd say that essentially, so if the tree looks like this, right? In terms of the original transaction hashes, let's draw 8 of them, right? And then this gets condensed down to 4. And then this gets condensed down to 2, and then this gets condensed down to the Merkle root, right? So what we're really saying is, so this was transaction 3, which is the one that we're trying to prove is part of the Merkle root. So what our full node has to do is to basically send at each point, at each level. So this is level 1, right? This is level 2. This is level 3, and this is level 4, right? If there are 8 original transactions, then there are going to be 4 levels. So at each point, we basically say, right, we know that this transaction is going to pair up with this one, right? And then those two are going to combine, and they're going to form this one. That's going to combine with that one and form this one. That's going to combine with that one and form this one, right? So as long as we send, if the Merkle path is basically to find transaction 3, is basically like this, right? Because these two are paired together. So we need to know this one in order to know what we combine with this one. And then we need to know this one to know what to combine with this one, right? So in this case, so you can see these are the nodes here, the ones I marked with the spot, which define the Merkle path. And the Merkle path is basically what the nodes that we require the full node to send the SPV in order for the SPV to validate that TX3 must have been used to create this Merkle root, right? So guys, thanks for watching. Hopefully that's somewhat cleared up what Merkle trees and Merkle roots are. And hopefully by now we're beginning to understand the underlying concepts of blockchain a little bit more. If there's any more questions, any questions at all, any feedback on what you'd like for future videos, please leave them down below. I'll try and answer them as best I can, and I will see you in the next video.